So our next chapter is the chapter of dimensions. Now let's take examples. Say radius of a circle, distance run by an athlete, length of a bridge. All of these are concepts of length. So we say all these quantities have the same dimensions. They denote quantities of the same nature. So they are said to have the same dimensions. So quantities of same nature have the same dimensions. So now in mechanics we have our three fundamental quantities: length, mass and time. And a dimension is denoted by a square bracket. So length, dimension of length is denoted like this: mass and time. And these are called fundamental dimensions. And any other quantity, a derived quantity, which can be written as some combination of these, will have a dimension which is some combination of the fundamental dimensions, from which we get our definition of dimensions. The dimensions of a physical quantity are the powers to which the fundamental units are raised in order to obtain the dimensions of that quantity. So from here we then come to dimensions of some standard physical quantities. Like for instance, area. Area is length into breadth or length into length or pi r square. So it's length into length. We write like this: L square, and we write it as m to the power 0 L square t to the power 0. Then we come to volume, having the dimensions of L cube, which we write like this. Then we have density, velocity, acceleration. Lt minus 2, force is mass into acceleration, work is force into displacement, so on, so forth. And so we have a whole list of physical quantities with their definitions and their dimensions that is given, which I will upload for you to learn the dimensions of all these physical quantities: angular momentum, angular acceleration, angular velocity, etc. and etc. Now in these there are some quantities which do not have any dimensions. For example, a number 1, 2, 3 has no dimension. So we write its dimension as m to the power 0 L to the power 0 t to the power 0. Similarly, an angle is also dimensionless. Arc length upon radius is definition of an angle. It's another dimensionless quantity. Similarly, quantity like pi also is a dimensionless quantity. Now, once we learn about dimensions, now comes the obvious question: what is the use? What's the use of learning about dimensions? First use is it can help us to convert from one system of units to another system of units. So if the quantity is n1 in one system of units, say it can be force, work, energy, whatever, and n2 is the amount in another system of units. So we write the dimensions in one system of units and the dimensions, and then we substitute the numbers for the different system of units, and so we get the value in the other system of units. And this is an example that is worked out over here, which you can see for yourself. The second very important use of dimensions is to check whether an equation is written correctly or not. Now when I write an equation x equals a plus b, or x equals a, the dimension of the left hand side of the equation has to be equal to the dimension of the right hand side of the equation. Also, when I add two quantities a and b, both quantities have to have the same dimension. Like for instance, we cannot add a length with a mass. We can only add two lengths or two forces or two accelerations or two energies. Quantities of same nature or quantities having the same dimensions. And the third very important use is using the method of dimensions, we can derive a relation between various physical quantities. Say, for instance, we want to express the time period of a simple pendulum. Now we don't know what it depends on. So we assume it depends on the mass of the bob, we assume it depends on the length of the thread, and we assume it depends on acceleration due to gravity. So we write time period is proportional to mass to the power A. We don't know how exactly it depends on mass. Length to the power B, G to the power C. And from here we say there's some constant of proportionality K, so T equals this. And then we write out the dimensions on the right hand side. Mass, length, acceleration LT to the power minus 2, left hand side is T, which we can also write as m to the power 0, L to the power 0, T to the power 1 is equal to m to the power A, L to the power B plus C, and T to the power minus 2C from indices, method of indices. And then we equate each fundamental dimension, the powers of each fundamental dimension, from where we get A must be equal to 0, and we get B plus C must be equal to 0, minus 2C must be equal to 1, from where we've already got A is 0, C is minus half, and so B is plus half. And so the time period of a simple pendulum is therefore K, m to the power 0, L to the power half, G to the power minus half. That's K square root of L upon G, where K is a constant which remains undetermined by the method of dimensions. And this is another example which I will show. So now this brings us to what are the limitations of the method of dimensions. One limitation we saw just now, that you cannot determine this constant which is supposedly dimensionless. You cannot tell what's the value of this constant. That is one defect or rather limitation of the method of dimensions. Secondly, if there is some quantity which depends on more than 3 physical quantities, then we cannot use this method of dimensions to determine the relation, because we have only 3 fundamental dimensions, so we cannot do this. And the third defect is if the equation contains trigonometrical ratio, sine, cos, etc., or exponential quantities or log, then it cannot be analyzed by the method of dimensions. So now I will also, there are some solved examples which I will upload for your benefit. You can just go through these solved examples, and once you do the solved examples, then there are some questions and numericals which I have given, which you can solve and submit as an assignment.